So now that we understand a little bit about specific heat, we're going to take a few minutes and talk about how we actually measure heat in chemistry. Remember, we're not measuring with a thermometer that measures temperature. And while they're related, heat and temperature are not the same thing. Here are your learning objectives for this video. Pause the video, write them down if you need to, and come back when you're ready. So before we take a look at the process, we want to understand a term that's very important. It's called enthalpy. And enthalpy is a quantity of heat change for a process, but also it's the direction that that heat is flowing, whether it's flowing into the system or out of the system. We calculate it by the equation delta H, which is the symbol for enthalpy, equals M, which is mass, times C, which is specific heat capacity, times delta T, which is the change in temperature. Now, you should recognize those variables and that relationship because it's one you already know. Delta H has the same value, the same number value, the same size as Q. The only difference now is that delta H will have a sign with it, either positive or negative. And the sign of delta H tells you which direction the heat is flowing. If delta H is positive, that means that this reaction or process is absorbing heat. It's taking heat in. In other words, it's endothermic. And if delta H has a negative sign, then it means that the reaction or process is actually producing heat, or it's exothermic. Now, where delta H gets its sign from has to do with the sign of delta T. And because we always calculate delta T final minus initial, if the final value, the final temperature, is less than the initial temperature, in other words, if the thing is cooling off, well, then it must be releasing heat, and delta T will be negative, and so will delta H. So your sign for delta T determines the sign for delta H, and delta T follows whether or not the thing is cooling off, giving off energy, or if it's heating up, taking in energy. So calorimetry is a process. It's an experiment that we can do that indirectly measures the amount of enthalpy in a system. Now, we can't just stick a thermometer or some other instrument in to measure the heat. So what we do is we use a device called a calorimeter, and it's usually something very simple. You'll see an example of it in just a second. But it's a device that's used to sort of get at the amount of heat in a roundabout fashion, because there's no instrument to directly measure the heat. We have to measure the heat when it moves. And different substances respond differently when heated, so we need a standard, and the standard that we use is water. So the simplest type of calorimeter that you're going to encounter is a couple of styrofoam coffee cups, maybe a lid and a thermometer, and something to stir them with. It's a very low-tech setup, but it actually does a pretty good job of capturing the heat. Now, the important thing about calorimetry is that we want to standardize, because all different substances react differently to heat, we want to standardize the experiment. And so the easiest thing to do is to use something that's the same in every experiment. So we use water. And water is a good absorber of heat because its very high specific heat capacity means that it can absorb a tremendous amount of heat before its temperature changes a whole lot. So it's a good heat sink, and so we use that in our calorimetry experiments. We can use calorimetry then to find changes in enthalpy, delta H. And since Q and delta H are the same, we have the equation already for calculating Q, calculating delta H. We just have to be very conscious now of the sign of delta H. So here's a picture of what a coffee cup calorimeter might look like. We've got a couple of nested coffee cups. You just double the insulation there by putting two of them together. We have a thermometer. We have an insulated stopper, but you can use any old cap. Plain old coffee cup cap that you might get at a coffee shop will do. The thermometer kind of goes through there into the solution because we need to measure the temperature. There is a relationship between temperature. And then something with which to stir. Honestly, when I build these things, I just use the thermometer to stir it. It's just easier. So how does it work? Well, here's our calorimeter, and we have our cover, and we have a thermometer and the stirrer, and our styrofoam cups, and inside the thermometer we have some solutions. Now, this particular type of calorimeter can only work with things that are in solution or things that are going to be in water. You're not going to burn anything inside styrofoam cups filled with water. It's just not going to work. If we have two reactants, we put them together, they're in solution. So two solutions, and we were going to react them together to create a chemical reaction. And we put them in there in the calorimeter, and the temperature of the water goes up. Well, that means that the water is gaining heat. It's taking heat from the reaction. And that means that the reaction must be losing heat. In other words, the reaction must be exothermic. So how does that work? Well, the energy that the reaction releases causes the water molecules that it's sitting in to speed up. And when molecules move faster, they have more motion. That means greater kinetic energy. So water is a good thing to absorb the heat, and we can actually measure the change in temperature of water. We also know the specific heat capacity of water, and we can measure the mass of water pretty easily. So we can figure out how much heat the water gained, and then that equates to the amount of heat lost by whatever's happening in the water. So we have to make an assumption. It's very important. We have to assume that the calorimeter doesn't leak energy or absorb energy from itself, because that would take away from our value. It's a pretty safe assumption to make with some of this. The error is not all that great. And there are some things we could do to fix it if we really wanted to, but we don't really need to. So the important thing to understand then is that the energy that's released by whatever's going on in this calorimeter is equal to the energy that is absorbed by the water in the solution. And that's the key to calorimetry. So here's an example. We have a hot piece of glass. We've heated it in a flame or something, and we're going to put it into a coffee cup calorimeter. And in that coffee cup calorimeter is 150 grams of 23 degrees Celsius water. So we've got some water in there. We measure the temperature, and it's 23 degrees. We put this hot piece of glass in there. We stir it with a thermometer or with a stirrer, and we watch, and the temperature goes up. Now, it doesn't go up very much, because water can gain a lot of heat before its temperature rises. But it does go up to about 26.5 degrees. So because the temperature of the water increased, we know that the water gained some heat. It took it from the glass. So what we want to do is figure out the enthalpy, the amount of heat that the water gained, and what direction it went in. Well, we know what direction it went in. It went into the water. And then we also want to figure out the enthalpy for the glass. Well, that's an easy one. So we're going to use our equation. Delta H is equal to M times C times delta T. Delta H is what we're looking for. That's the enthalpy. M is the mass of the water. C is the specific heat capacity of the water. And delta T is the change in temperature of the water. So to calculate the enthalpy of the water, I take 150 grams. That's how much water I had. The specific heat capacity of water is 4.184 joules per gram degree Celsius. And then the change in temperature. Final temperature was 26.5 minus the initial temperature, 23.0. So I get 2,197 joules. That's the amount of heat that the water gained. Well, if you remember, where did it get that heat? It got that heat from the piece of glass. So the enthalpy of the glass is the opposite sign from the enthalpy of the water, because the glass lost the heat. It's exothermic, and when it's exothermic, delta H will have a negative value. So delta H for the glass is negative 2,197 joules. So we didn't even have to really measure anything about the glass. We just put it into the water. We did all the calculations about the water, and we got the information about the glass. That's what I mean by an indirect method. It's not directly involving the substance. It's using another substance to help us out. That's how calorimetry works. Now, what if we want to burn something, though, and we want to figure out how much energy is coming out of something that's burning? Well, we can't do it inside water because water puts out fires. There's another way we can do it, and that's what our lab is going to be. So, give it a try. Run through it again if you need to. We'll get some practice in class. Good luck.